My name's Andrew Ferlitsch. Okay, I'm the author of Deep Learning Design Patterns. Okay, being published by Manning. As far as my current background, I work for Google AI. I'm in Google Cloud Developer Relations. Okay, I'm primarily external facing. Okay, so I work. I'm external facing, meaning I'm outside of Google. You'll find me, like, for example, at conferences, doing presentations. You might find me, doing training sessions for Google and Google Cloud AI's products. I work quite frequently with Google's enterprise customers, helping their teams get AI working at a large scale. It's actually one of my specialties is doing AI at a very big production level. And occasionally, I'm also an adjunct professor at universities. Prior to that, I worked in Japanese IT for 20 years. I was a principal research scientist. My main area was imaging. So you can see the relationship between imaging and AI with convolutional neural networks. It was kind of a normal transition. I actually have a graduate degree in artificial intelligence. It's back from 1987. It's dramatically different today. So I bring in a lot of diverse background behind AI. Okay. So today, I didn't really know what's the best way of doing this on Twitch. Okay. Here's some things I didn't want to do. I have massive amounts of training programs that are pre-recorded. They're there on YouTube. I didn't see any reason to repeat content you've already seen. I'm also not kind of the guy who's going to sit online for a couple hours and just be coding. That seems kind of like really dry and technical. So what I decided to do is, in writing my book, I got a slide deck for all my images and figures. There's actually several hundred. And I'm going to just take a small section of those figures that you'll find in my book and walk you through them, kind of give you an idea of what to expect in the book. Okay. So a little bit more background. The book doesn't start like at square zero. It assumes you have some experience with machine learning. You're kind of at that beginning junior level as a role. You're employed, generally job titles are ranked like junior, intermediate, senior, or advanced, or architect. Okay, so the book starts at that junior level role. Okay. For those who feel you need a little bit of what we call a primer, okay, to sort of get up to that, we have a primer that's available free that precedes the book and has 3 chapters to sort of get you up to speed so you can start on chapter 1 in the book. And fairly early on in the book, we talk about how in the last few years advancements in neural networks of all types have moved rapidly by the adoption of design patterns. Okay, many of you have likely got a background as a software engineer or an software application writer. Okay, and assuming that you're familiar with OOP principles, it's kind of when the idea of design patterns came about. It really was coined by a book written by what was referred to for people as the Gang of Four in the 1990s. And it really just said is, if you have this problem, use that pattern. If you have this problem, use that pattern, so forth and so forth. And that's what's happened to deep learning. Okay. And today I'm going to cover one of the most elementary design patterns in deep learning. It's really one of the first ones to emerge. There's multiple variants of it. The one I'm covering, the idiomatic procedure reuse one, is one that was rendered by me. Okay. So I'm the actual original author of this design pattern. And in my book, I can actually show you the flexibility of the design pattern can actually be retrofitted or reapplied to the past, to state-of-the-art architectures like AlexNet, VGG, ResNet, etc. All those really, Inception, all those really famous ones can be repackaged in this design pattern and written really simple and quick. Okay. Depending on when you got into deep learning, if you go back to about 2015, we didn't have these high-level deep learning frameworks like TensorFlow and PyTorch. We had these really low-level frameworks like Caffe. And those original state-of-the-art models were mostly written in Caffe, and they were extremely cryptic to read, and they were written in what you would call a batch style, meaning they're just written linearly, line by line by line by line, and there's no reuse. Okay. When you have a design pattern, it implies there's a pattern, and that pattern's repeated over and over. And being good software engineers, if you have a pattern that's repeated over and over, you make a procedure or a method out of it for reuse. Okay, so that's kind of the background here. Okay, I'm just checking if anybody's got any questions at the moment. I don't see anything. I'm just kind of curious how many people are online today. All right, okay. All right, so fundamentally in a convolutional neural network, we break it down into components, okay? And traditionally, there are three major components, okay? One is referred to as the stem, the other one's referred to as the learner, and then finally as the task. And the stem, the simplest way to do is it's going to take those images you have, okay, and it does sort of the first coarse level extraction of features, extremely coarse level, and then sizes the feature maps that are going to come out of it, the number and the size, to hit a target here, okay, which I'll describe later. The job of the learner is to do what we call feature learning. It wants to learn the features that are in the image that it's going to need for prediction, okay? And then at the very end of it, you're going to have what's called the latent space. And we'll go more into that. And the latent space is something that is dimensionally substantially smaller than the input here. But from that latent space, it holds the important features we need to know. And you can think of everything else that's in the picture we don't need, if you want to think of it that way, has been thrown away. So we can focus only on the important things. And then there's finally a task group. And that's where you're going to do the task learning. And for example, you're going to learn to classify what the image is. Or you're going to learn to locate different foreground images within the picture, put a bounding box in it and classify what's in that, like object detection. Or you might do image segmentation, where you're going to actually identify every pixel of what it belongs to. Okay, a simple example might be medical. So you got a chest x-ray, and you're looking to say it's cancer, and which pixels are the cancer and which pixels aren't. Okay. So I'll just move on to the next slide. So it's kind of advanced a little bit with TensorFlow 2x. We brought in this concept of moving data preprocessing into the model itself, and it provided new layers for that support. And we refer to that now as a pre-stem group. Okay, so if you look today, our modern convolutional neural networks are designed to take data preprocessing into the model. The reason for this is just a lot more efficient. Historically, data preprocessing, like resizing your image or normalizing the pixels, and again, I'm assuming in general people have know the basics here, happened upstream from the training on a CPU, and you did your training on a GPU. The problem is, if the CPU couldn't preprocess that data as fast as the GPU could consume it, you would be starving the GPU. Think of the GPU as an engine. If you're not feeding it as much gas as it can burn, it's not running at its full performance. The problem gets even worse when you go to multiple GPUs. You're even more likely to starve it and have to go to bigger and bigger CPUs. So it just made more sense to move the data pre-processing into the model. And these are called pre-stems because they actually generally don't stay with the model. They're there during training and then removed afterwards. There are some pre-stems nowadays that we keep with the model, but in general, they're like plug and play items. You build your model, then you have this collection of pre-stems and you snap one on for the training. When it's trained, you break it back off. Okay, so this kind of I guess some of these slides are probably, these are just different pictures you're going to see in the book, okay? So another thing I'll highlight in here, the learner consists of what we call groups or convolutional groups, okay? Typically, every group consists of one or more what are referred to as blocks, convolutional blocks, okay? And those blocks implement a certain pattern. Okay, and what the groups do is they're going to modify, say, the parameters that go to that pattern. Typical parameters would be the number of filters in the convolution or the output size of the feature maps. So I look like somebody's got a question. Okay, actually not a moment, just somebody saying hello. Okay, all right. Okay. Go on next. Okay, so let's kind of look probably at the next picture here. I think it takes a deeper look at what's inside of a learner. Yep. So the learner is really where the bulk of the model is. Okay, and these are convolutional blocks. Oh, this is a group, excuse me. So we were up here. So I said you got these convolutional groups, okay? They have parameters that they're going to pass down to their blocks. And each one of those is made up of a sequence of blocks, okay? So when you look at, those older diagrams from research papers that reappear in blogs and all that, that low-level pattern that they're showing, that's a convolution, generally referred to as a convolutional block. Okay, so the style is also useful for models that do more than one task. Okay, so you generate, like the simplest convolutional model, it just predicts what the image is. Is it an apple? Is it an elephant? Is it a car? Okay, the next level up is what we call a multi-label CNN. Okay, or a multi-category, and that is going to predict multiple labels for it. Okay, so it might say that's an apple, it's the color red, and maybe it says ripe. Okay, well, each one of them is a separate label and needs a separate classifier. Okay, and those are your tasks. That's what you want to learn. I want to be able to learn what type of fruit it is. Okay, and then I want to learn what color the fruit is. And then I want to learn the ripeness of the fruit. So you would have 3 separate tasks that you would train as part of all this. But it wouldn't change your model. All of this is reused for each one of these tasks. So again, you're going to see in the idiomatic pattern this high level of reuse. Okay, so this is just sort of zooming in on that last little picture there. At the end of a learner, when you look at the idiomatic pattern here, you have a final set of feature maps. There tend to be a high number of them. For example, in ResNet, you'd have 2,048, but they're all really small, somewhere between 4x4 and 8x8 pixels. Okay. And what we finally do is we have what's called, when we come into the task component, and we're going to learn the task instead of learning the features, Okay, the features we have learned, we're going to do this really massive dimensionality reduction on it. Okay, we're going to pool it down into a 1D vector of a smaller dimension than the original maps. Okay, and that's referred to as our latent space. Okay, and from that latent space, that's much dramatically reduced dimensionality, okay, is what is going to be used as the input to all the different tasks we want to learn in parallel. Okay, so I'm just going to jump ahead a little bit so you know what I mean by tasks in parallel. Another really one of the granddaddies of them all for what we call a multitask model, that is a model that learns more than one task, is object detection. Okay, so what it's going to do is it's got to go through and propose bounding boxes throughout the picture. And there's various algorithms for doing it, but there's some set of candidate bounding boxes. And then for each one of them, it has to decide whether it's a foreground or a background. Foreground meaning there's an object in it. Okay, so then those candidate bounding boxes that are being deemed as foregrounds go through two separate task learning. One has to learn what's in that bounding box. That's the classification. And the other one learns to tune the bounding box around that object. And I'm going to back up a little bit here too. For those who are software engineers or came up as software engineers, you can see the concept of components here in your design. We have three components: a stem, a learner, and a task. And you can see the procedure reuse that's occurring inside the learner. And okay, any more questions? I'm just checking here. Okay. Okay. So as things evolved over the years, in the last few years, we've introduced this concept of meta parameters to models. I'm going to assume that all of my listeners here are generally familiar with models and how to train them, and are familiar with the words parameter and hyperparameters. So parameters are those weights and biases inside the model. It's what the model learns, and they stay with the model. And then the hyperparameters are those things we use to tune the training of the model to get the best result out of it. Things like the batch size, or the learning rate, or the learning rate scheduler, or the layer regularization. Okay. But they don't stay with the model. Okay. Now, meta parameters is like, it goes a step further, is now that we're designing our models as patterns, and those patterns take parameters, the meta parameters are like the configuration. Think of it as a specification. A standard model design is kind of like a factory now, and you can think of each one of these convolutional groups up here is like a station in the factory, and it has certain patterns that it can produce at that factory point. Okay, but there's some variability in it. Okay, and so what you do is you pass in a specification that gets pushed down to the machines, and they produce that item, right? Conceptually the same thing here. That's what meta parameters do. Okay, typically the meta parameters might specify like the number of blocks that are going to be in a group, and then for the group, the number of input filters, and optionally the number of output filters. So in some convolutional groups, it's generally a convention in most models that every convolutional block in a group has the same number of filters. The one exception we see in there in some state-of-the-art models, or I call them SOTAs, okay, is that you have one number for input and one number for output. Well, the output one only applies to the last convolutional block. Another thing that sort of evolved starting with 2015, and it's pretty consistent now, Early convolutional models, we called them covnets, okay, because they had one simple pattern: convolution, pooling, convolution, pooling, convolution, pooling, okay, and pooling is a reduction step, okay. In modern models, we delay the pooling or the reduction, okay, dimensionality reduction, to the end of a group. So it only happens once in the group. It doesn't happen in the blocks. There are some state-of-the-art ones that do it at the beginning, but the majority of do them at the end. But the important thing is it happens only once in a group. Another thing that you see is common in models and fits well into the idiomatic design is the idea is that there's more than one type of output from the model, okay? You know, the easiest way you can think of, an image classification model is at the very end. Let's say it has 10 classes. Maybe we're talking about minced, okay? So 0 through 9, and for every class, it predicts its confidence. I'm 97% certain this is a 1, and I'm like this minuscule, 1% or a quarter% or a tenth of percent. I think it's a 2 or a 0 or a 4. Of course, and the one with the highest number is the prediction, okay? And that's called your softmax post-activation output, okay? But before we put it through a softmax, every one of them was an independent prediction, okay? They didn't necessarily add up to 1, okay? And it turns out that type of output, the probabilities output for these hard outputs, okay, think of these as the soft outputs, these are the hard outputs, are useful for other things like knowledge transfer, okay? If we back up even more, okay, we're now getting into the latent space, okay? This is the latent space here, okay? And we have two aspects of it. Before we did the global average pooling, we did that massive dimensionality reduction. Our latent space is still in a high dimensional encoding. And after we've done that big reduction, we're in a low dimensional embedding. And that's also known as feature extraction. If you go to TensorFlow Hub, okay, and you ask for a model with the attribute feature vector, okay, that's their word for feature extraction. It's called feature vector. Your model is working on this output, okay? And if we look back up here, the input to these is that encoding, okay? So it's important today so that we can snap different, just like I showed earlier, snapping different pre-stems on. It's also important in our models we can snap on different types of tasks to learn. And depending on its task, it may take its input at a different stage. And so nowadays we're coding our models to have these 4 different stages in them so we can reuse them for different outputs. Let's see if anybody has a question. Oh, I don't see anything yet. Okay. Hopefully everybody's enjoying this. It's kind of just free form here. Okay. Okay. So here's an example, a real world example. Let's say you wrote a model that's for insurance companies, and it takes a picture and it's going to estimate the damage, how much damage is there in dollars to repair, okay? Well, we got kind of a problem because there's 2 types of damage. There's major damage, which is really obvious, a crumbled up side of the car, a broken windshield, etc. But then we also got minute damage, a ding, a scratch, a little crease, stuff that's hard to see with the eye. And obviously the major damage would overwhelm the minor damage. If we had a model, we just simply try to train for both, okay? So the way we do it is we know with the major damage, it's so big that it's easy to spot. And so we can just go ahead and use the encoding, which is at the low dimensionality, so it's much smaller, much more efficient, and use its output to train to look for major damage. On the other hand, the little stuff is so small, it probably would get lost in this dimensionality reduction. So we want to use the earlier stage, the encoding, where it's of high dimensionality, and we can still spot things like a ding, a scratch, etc. So if you looked at a model, if somebody was writing this model, they would have their normal model here, and they would completely reuse it. Notice no tasks here. You get to this last stage. This is the latent space, and there's going to be two outputs from it, and they're going to be hooked to two separate task learners. One's going to learn the minor damage, one's going to learn the major damage. Nobody would write two separate models to do this. I'm not sure, there was a question here about scikit-learn. I'm not sure, there may be stuff in, scikit-learn traditionally. I mean, I used it years ago when I was doing just mainly, structured data. I was really good at structured data. I'm a convolution imaging person, so I don't really work with scikit-learn, but I work with things like TensorFlow and TensorFlow Keras. That's just one of the questions I see in chat. Okay, so I kind of talked about this idea of pre-stems being plug and play. Okay, so if you're in production in MLOps, this is pretty common now. So you have your standard model here, as I kind of showed you. Just remind you it has a stem coming into it. Okay, and then you're going to have all these pre-stems. They're kind of like a library. It'll do different things. So in imaging, you probably have one for some form of, pre-processing the pixel data. First, you might resize the image to match the shape that the model takes. Okay, so let's say your model takes 128 by 128. The pre-stem may take an input tensor that's unspecified for height, width, anything can come in, but then resizes it to 128 by 128. But it's still all integer data. We need to convert it to float, and we'd like to normalize it, where every pixel is in a range between 0 and 1. So that all could be done in a pre-stem. Okay. Another thing we might do in a pre-stem is handling what we call translational invariance. And this is training a model that the object you want to classify in the picture, it doesn't matter where in the picture it is or what orientation it does. And historically, we've done that through data augmentation, or more specifically, image augmentation. Again, many of you are probably familiar with that. You take your set of pictures and you're going to make sort of on the fly copies of them with some modification, like you might flip the picture, or you might rotate something in the picture, or you might shift it. Okay, all that augmentation, what it's doing is it's assisting the model in learning translational invariance. Okay, and the word invariance here, if you're not familiar what that means, it just means that it's invariant to some change. The predicted outcome doesn't change to some change in the input. Okay, in this case, translational. And translational just means its location orientation in the picture should not change the predicted outcome. So that's where the word translational invariance comes from, and that's why we do image augmentation. Nowadays, we can build image augmentation as a set of layers and put them in a pre-stem, and you can pick and choose which types of invariance you want to do. It's not just translational. You got scale invariance. There's all different types of invariance, and just pick and choose and snap them on. Your ML ops person is just snapping them on as the model is being trained, and then pulling them off when it gets deployed. Can a CNN be used for sales forecasting? Okay. That's a question. Now, this is an interesting one because typically sales forecasting is a time series type of thing. That's a special form of structured data training. But there are some tricks where you can convert a forecasting problem into an imaging problem. Okay, but in a sense, by doing a domain transfer of the input. I did this for COVID. Google asked us AI people to volunteer our time to aid in the research of COVID. And one of the areas I looked at was, trying to forecast out daily counts, and globally, not just for the United States, but all across the world. And, what I had for data is the Johns Hopkins data. Okay, and of course I have daily counts. At this time it's probably April, so I've had a couple months of daily counts from all over the world. And I kind of, when I plotted them, they kind of look like sort of a warped normal curve, or those are older, a Gaussian curve or a bell curve, but not really quite. Okay, I think of it as the other end has a long tail. Okay, and so what I did is I converted it into a visualization problem, right? So I just took those bar charts. So you take the data, I plot it to bar charts. Okay, well, that's a picture. Okay, and what I would do then is I want to train it on tomorrow, to predict tomorrow. So I take for every training, every image that went through through the CNN. So they're both bar charts. You could say yesterday's bar chart, and the label would be tomorrow's bar chart that would have one more bar on it. Okay, and so it looked pretty good. Of course, it was still too early for anybody to really have any model to accurately predict. But it is a different way of doing time series using a convolutional neural network. And thanks for the question. Again, this is just being really informal here. And those are the kind of examples you would find throughout the book. How do you apply this stuff? Okay, there's nothing there. I'm going to probably skip AlexNet and just go to VGG. Okay, so let's go ahead now and take this procedure reuse design pattern, okay, and apply it to some early state-of-the-art models that were put together in Caffe and had no pattern at all in their design, okay. No, I can't say no programming pattern. They had a model pattern, but not a programming pattern. Okay. When you retrofit it, you can make a VGG looks like this. It actually has a stem. It has a classifier group in it. And this entire interior can be broken down into 5 convolutional groups. And if you remember, generally every convolutional group has the same number of filters. So you can see 64, then 128, then 256, 512, and 512. And this progression is actually fairly common from BGG. Most convolutional neural networks, every subsequent group will double the number of filters than the last. That's the general rule. Of course, there's always exceptions. Okay, what we say is between the stem and the end of the last convolutional group, that is where we're doing our feature learning. And in the case of a image classification, the task group is where we're doing our classification learning. Of course, we could learn any task we wanted to. And so generically, that would be called task learning. Okay. So in a VGG, a convolutional group actually didn't have blocks. It was just a sequence of convolutional layers, of one or more, and then ended with the concept. They were probably the first to bring up the concept of delaying max pooling to the end of a convolutional group. I think this is about 2014. Yes, be 2014. They had just a horrifically large classifier. Nobody does it anymore, where they put in 2 dense layers of 4,096 parameters each. Okay. Yeah, that's really freaking ridiculous. For it just causes a computational explosion, and it turns out unnecessary. Matter of fact, as long as the latent space is the right size and it really has the important features encoded in it, in modern ones, we completely drop this, and we even further reduce the latent space coming in, and we can learn just as well. But this was early days. They didn't know any better yet. Okay, anything here? Yeah, I'm not going to go too much there. Okay. Yeah, if you're not familiar with the idea of a stem too much, remember I said that's where it does the first feature extraction and prepare course level feature extraction, and it sort of prepares a certain number of feature maps and sizes, such that when it goes through all those groups in the learner, when it gets to the latent space, they're all of a certain target size. Okay, the ideal target size. Not too small, not too big. Okay, so here VGG was really simple. It was a single 3x3 filter, a kernel with 64 filters. So if you looked at it, you had an RGB image coming in, say it was 224 by 224. What's the output is? Now you have all these individual channels. These are channels in an image. There's a red channel, a green channel, a blue channel. So filters, while we call them feature maps, they're also called channels. So there's 64 feature maps or 64 channels, and they are of the same size. Yes, somebody's asking about a stem and an NLP. That's your encoder. Okay. Think about what you have to do today in natural language processing. Okay. Your input isn't the text string. Okay. It's still a vector with numbers in it. And that text string has to go through a trained encoder that's going to make a vector, like a word vector. Okay. That step is a stem. Also, it has to be, all the inputs have to be the same length. So if you worked in NLP, you know about clipping and padding. Okay, so if your batch is going to be, say, each sentence is going to be 20 words, then any sentence over 20 words, the remainder has to be truncated. And anything shorter than 20 words, the missing ones have to be padded. So they all have the same fixed length. All that preparation, that step, is the stem in a natural language, in NLP. But thanks for the question. Good question. So let's go ahead and look how this is sort of, you can take this procedure reuse pattern, hammer it into ResNet. Okay, and while I'm not showing any code here, at my repo, okay, you'll find I have a folder, it's right at the top level, called Zoo, and right underneath it I have renderings of, I don't know, about 50 state-of-the-art models in all kinds of design patterns, including the sort of granddaddy of them all, the Idiomatic. Okay, so ResNet, again, followed the same pattern here. You know, it has a stem, convolutional group. It has a learner, though they refer to these now, instead of convolutional groups, as residual groups. It's just a terminology they used in their paper. Okay, and then you had your task group, and notice they were one of the very first ones to drop having all those extra dense layers. Okay, but at this point, you know, you're up to about 2015, we still think of a model as having two major sections, the feature learning and the classification learning. This would evolve too, by the way. Okay, so what made ResNet unique? Okay, so in their paper, they started off what they called a ResNet 34. This number is actually the number of layers. And let's kind of maybe back up saying what problem they were trying to solve at the time. Okay, so early on, 2012, 2013, 2014, the models that were winning ImageNet were, obviously each year they got more accurate, but they got more accurate by going deeper in layers. But they ended up, back in those early days, hitting a limit. Okay, and the problem is that these parameters and inputs coming into the models are generally between 0 and 1, meaning there's small numbers smaller than 1. And you're doing matrix multiplications. So when you multiply one number smaller than 1 against another number smaller than 1, you get an even smaller number. And if you keep propagating that deeper and deeper and deeper in your model, you get smaller and smaller and smaller numbers. Well, the problem is our hardware is discrete, okay, and it approximates the representation of a floating point number. And if that number gets so tiny, the hardware can't represent it anymore. It becomes not a number. Okay, and that's actually what a vanishing gradient meant. It just meant the hardware couldn't represent it anymore. So they needed to come up with techniques to keep that from happening. And the identity link in ResNet was one of the very first ones. Okay, so VGG only went up to 19 layers before it started having the vanishing gradient. With this design, they were able to get to 34 layers and get more accuracy. Okay, and what they did is they made a block of a stack of 2 3x3 convolutions. You'll find in modern models the idea of a stack of 2 3x3 convolutions is extremely common. Okay, and the idea was that every time I went through a block and generated a new set of feature maps, I've kind of lost any memory of the past. I've thrown away the past, and here's the new representation. It goes through another block, right, which transforms it into yet another representation, but I throw away the past. And the idea is, what happens if we could try to remember something about the past, not completely throw it away? And would that help us stabilize these numbers? And it turned out that it did. Okay, so what they did here is, this is your block, here's your input coming in, is they just made a copy of that input. So this is the original input, here's the transformed output, and they just did a matrix add of the original input to the output. So that doesn't add any more data. Okay, but think of it this way, let's oversimplify it. Let's say in here your output was, your matrices were all 4s, values of 4, and the input was a 1. Well, 1 plus 4, what would come out is now they'd all be 5s. Okay, I'm going to check the questions. All right, to see how people are doing. Okay, we still got a fair number of people on. Feel free to ask questions. Okay. So the ResNet learner, consisted of 4 convolutional groups. Okay. All but the first one they referred to as strided, meaning that the strided just means there was a dimensionality reduction step in it, or what you might call a in modern terminology, didn't exist then, be called a reduction block. Okay. The reason the first group didn't have it is they already did the corresponding reduction in the stem. Okay. ResNet also was one of those branches of models that did just like all of them, did delayed pooling or delayed reduction, but in the case of ResNet, they did it at the beginning of the group instead of the end of the group. Okay. I take that back. That's a different, I think that's a ResNet. I did that. They still did it at the end of the group. Been a while since I've read all these papers, as you might guess. All right. So, a ResNet 34 consists of a sequence of blocks. And then at the very end, they had what they called a convolutional block, meaning there was no identity link, where they did a matrix add of the input to the output. So just sequential convolution. Okay, if I recall, it was probably just a single convolutional layer, but it did a dimensionality reduction. Okay, that is, it decreased the number of the size of the feature maps. So it would have been what's called a strided convolution. If you're not familiar with that term, that means your stride for moving the kernel across the image is moving 2 pixels at a time instead of 1. Okay, and if you move 2 at a time, then the output will always be 1/2 the height, 1/2 the width of the original input. And of course, this is a matrix, so that's not 1/2 reduction in size. That's 0.5 times 0.5. So it's so the output size is 0.25, or you're reducing it 75%. Most modern models, after every group, they doubled. Each group doubled the number of size of feature maps. So here you can see in this ResNet 34 design that convolution, and in addition to doing that dimensionality reduction, the deferred pooling, it also doubled the number of output maps as the input to the next group. Now, you could have designed it differently and made the first step in the next group the doubling. Okay. All right. So I'm going to just cover a little bit more ResNet, and then we'll probably move on to some other things. So the one they took to the contest, okay, appears as figure 3C in the paper, and they won, was what they changed the design from what would have been a 2 3x3 convolutional layers to a 1x1, a 3x1, and a 1x1. Okay, and this is referred to as a bottleneck design. Okay, and if you think about it, think about the top of a bottle, how it kind of curves in, okay, and so you got that top funnel sort of squeezes things down. Okay, and that's what a bottleneck does. So they're going to do a 1x1 convolution to do a dimensionality reduction, then do the 3x3 convolution on that space, okay, that reduced dimensionality, okay, and then a restoration step, a 1x1 convolution to restore the dimensionality back to what it was at the input, okay. 1x1 convolutions are very common nowadays in models. When people first see them, they always ask, what can you do with a 1x1? I mean, moving a 1 pixel window across 1 pixels, what's there to learn? And in some sense, you're right. You're not going to learn features. So there's 2 types of them. There's one that's used to reduce the dimensionality of the input, and that's called a 1x1 bottleneck convolution. And then there's another version that's used to expand the dimensionality of the input, and that's called a 1x1 projection or linear projection convolution. Is there anything else worth looking here? Nah, probably not. The stem was ridiculous in that early one. Okay, so let's kind of look at Res next. Okay, so ResNet would have came out of Microsoft, and if I recall, ResNext, did it come out of Microsoft? It's been a while. I'm trying to remember if it came out of Microsoft or Face++. I'll have to look that up. It's just been a while. Okay, but ResNext was sort of the next extension to ResNet. It was almost entirely the same. Okay, conceptually, it's the same architecture, but instead of being residual groups, they're residual next groups. Okay, everything else is the same. Okay, the construction of their groups were the same. Okay, what changed was a single modification to the bottleneck residual blocks. So if you remember in ResNet, we had 1 by 1, 3 by 3, 1 by 1. This was in ResNet a normal convolution, and they replaced it with a group convolution. And I'll go in a minute what that looks like. Okay, right there. Okay, and so it's a little bit hard for people at first to grasp. So you're used to taking an input, all your feature maps, and passing them as a batch through a single convolutional layer. Okay, well, in ResNext, they introduced this concept of going wider, okay, to increase accuracy instead of going deeper. Okay, and the way they went wider is this operation they called split, transform, and then merge. So they take your feature maps and they partition them up, okay, and you define how many partitions you're going to have in a group. So let's say 8, okay. And let's say you have, for simplicity, you have 80 feature maps coming in. Well, if I'm going to have 8 partitions, each partition in that group is going to have 10 of the feature maps. So the first one's going to have the first 10, the next one's going to have the next 10, the next 10, the next 10, and so forth. So that's the split operation. Then each one of those, you could say, mini sets of feature maps goes through a separate 3 by 3 convolution. So in this case, if there were 80 with 8 partitions, I got 80 feature maps with 8 partitions. Each I'm going to have 8 groups or 8 partitions in my group, 10 feature maps each. Each one of those would go through its own 3 by 3 convolution in parallel. That's what they call the transform. And then I'm going to take all their outputs and concatenate them back together as if they had all, as a single batch, gone through a single 3 by 3. And that's the merge operation. And that's the only thing they did different. See if anybody's got some questions. Okay. All right. Okay, what else can we look at? Oh, there's plenty of slides here. Yeah, the other thing was kind of a little bit different in ResNext, even though conceptually it's the same as a ResNet with that one change in their paper. How they showed the delayed pooling, they actually pulled it out as if it was a separate step, even though it's really still the last step in a group. And they just did it with a strided convolution, just like they did in ResNet. It didn't change. Okay, so maybe we'll take a moment, look at SENet. Okay, so again, an SENet is an adaptation to existing residual models. So assuming you already have a residual model, a block design model like a ResNet or a ResNext or an Inception, this is something you added to it. So it wasn't really like a new architecture, but a modification to existing architectures. Okay, and this kind of show you what that modification is. So assume this residual block is that original residual block we're talking about, but without the identity link. So if we were talking about the bottleneck one, the 1 by 3 by 1, this is the 1 by 3 by 1. We got that output. But instead of that output going straight to the add, matrix add, and the input, of course, being added to it, is we insert a step in between. And that's called the SE block. And I see there's a question. Okay. Okay, so is there an URL that lists all Manning's publications, live events? I think it's just their Twitch channel. I'm new to Twitch, but this is what they gave me. Let me double check. I think it's just called Manning. I'll just put it here in chat. Okay. And actually, we can just go up there for a minute. Okay, somebody's looking for something on Linux SE. Okay. Obviously, this isn't the same SE. So SE here, by the way, stands for squeeze and excitation. That's what they refer to it in the block. Okay, so let's kind of go down to the theory behind it. Okay. What they wanted to do was make the information that is being matrix added sort of more valuable or more magnified, that it would retain what they refer to as feature reuse deeper into the model. So again, you could go more layers and increase accuracy, or get more accuracy out of the same number of layers already. Okay, so let's go ahead and just, here is that little excite link. So remember, this is the residual block output without the identity link. Okay, so you got that batch of feature maps coming out. They have some shape, height by width, by channels, the channel being the number of feature maps. And the first thing they did is they did an aggressive reduction on that, making it into a 1D vector, the length of the number of feature maps. So if you're not familiar with global average pooling, regardless of the size of your feature map, it's going to replace that whole feature map with one value only, and that is the average of all the pixels in that feature map. Okay, so that's quite a reduction. Okay, then they reshape it here and put it through a dense layer, which does a compression, a further compression. Okay, so the number of nodes here doesn't even equal the number of channels, but some reduction ratio. So this is squeeze, squeeze, squeeze down. Okay, and then they do another dense layer to restore it back. Okay, so now what I got is, I really got this 1D vector long, where the number of elements in the vector is equal to the number of feature maps, the same number here. And I'm going to do a matrix multiply of this single value across that entire feature map. So here, that you could say that matrix multiply operation is broadcasted. Okay, and that's their excitation. They're going to just add a tinge more of the assumption here during the squeeze. Is anything really not important would have gotten lost by this aggressive squeeze. So anything that's still here at the other end must have been important. Okay, and then by doing you think of it as a mask, by doing a matrix multiply, those spots in those feature maps that have the importance thing get increased a little bit, sort of like a little bump, an extra emphasis, and that is the excitation. And on average, at the time when they came out with this, it added about 2% more accuracy to existing models. Okay. All right. Okay. Yeah, let's look at DenseNet for a moment. This one was also kind of confusing to people because it had this principle where the outputs of one layer are shared with every other subsequent layer. And that always looked kind of complex, that link structure, and it's really not. It's actually really easy to write. Okay, I'll give you a hint. Replace the add operation with a concat, and effectively you have you convert a residual net into a dense net. Okay, the problem with that concatenation, of course, is the number of feature maps can grow rapidly, practically exponentially as you go deep, sort of undermining the model, making it explode in parameters. So you need to do aggressive reduction at the end of each group. And again, in the case of the authors, always referred to that as if that was a step separate than the group. But conceptually, since it follows every group, it's still the convention that your reduction, your delayed pooling, is done at the end of every group. It's just a lot more aggressive in a DenseNet because of the concat operation replacing the add operation. So let's kind of see if I find a good picture that would show that. Right there. Okay. So here's how it works. If you remember, in the residual block, we have the input, right? The output comes out of the block, and we make a copy of the input, and we would add it. This time we're going to concatenate it. If we did an add, we'd have the same number of feature maps. So 64 came out here after the matrix add, you still have 64. But when it concatenate, we're going to double it. It's now going to be 128, right? We put it in the next block, it's now 256. Put it in another block, it's now 512. So, oh boy, this thing is just growing really rapidly. Okay. Now the advantage, of course, here is the input is always being, from every layer, gets reused at every other subsequent layer. That's the concept behind a dense net. But at the end of each group, those maps, we have so many of those maps that we got to somehow take control, right, of that parameter explosion and have what they call a transition block, which is really today's terminology be a reduction block, and really squeeze it back down to control the size of the number of parameters in the model. Okay, don't see any other questions. Okay, let's see what else might be interesting. Yeah, just shows that. It's really, the same as a residual block, but we got a concat there instead of an add. There's something here. Okay. This is just another kind of type of picture you might see. I want to look at different things here. So here's an example where we talk about having this is the dense net. I see what it is. So you have this convolution. It's a 1x1. It's doing what's called a linear projection or dimensionality expansion using a linear projection. It's increasing the number of feature maps by 4 times. Okay. And then we do a convolution on that reduced, on the original number of filters. So that would be referred to as a bottleneck convolution. Conceptually, this is what it would look like, right? So here, assume these are my inputs. Let's say I got 4 feature maps coming in. I do that 1x1 linear projection step times 4. This right here. Okay, so its output would be 16 of these, right? Then I do my 3x3 convolution, which also does a reduction because it goes to the same number of filters, 4. And so its output now is the same size as the input. See what this next one was. This is probably referring to a transition block. Okay. So one is, so the way they reduced is they did it in 2 steps. First, reduce the overall number of feature maps and then reduce their size. So the first thing they did is a 1x1 bottleneck convolution, reducing the input to 1/2 the number of feature maps. So in this case, I think I showed 8. Gets reduced down to 4. Okay. Oh, that was configurable. That's called the compression factor. So in this case, if I put 2, I got half as many. And then they did average pooling on it with a stride of 2, which produced outputs that are 1/2 the height, 1/2 the width. So that's how they did their more aggressive reduction. Okay, just looking if there's anything more. That's just a comparison. I got pictures for everything here. Okay. When you get to mobile nets, the primary difference in their structure, they're very similar to their, say, bigger cloud ones. Okay, they're going to have fewer layers because they have to fit in the memory, and they're going to use convolutions that are more efficient. They may not be quite as accurate, but they're substantially more compute efficient. Okay, and so typically, instead of seeing normal convolutions, you're going to see depthwise separable convolutions, and that really got pioneered in 2 places. One of them with the original MobileNet V1. Okay, which I believe was around 2016, and at the same time, Francois Cholet was showing how they could be used also in a large model when he designed Exception. The classifier group is not implemented in the conventional manner using a dense layer for the prediction. It actually uses a convolutional layer, okay? And that's pretty standard today for mobile nets. Okay, so I'm going to skip a bunch of stuff here. Probably covered enough in networks. So let's find something a little more interesting. I'm just spinning way down here. Oh, okay. So let's kind of look at different architectures in a standard classification. Let's try to get a little more interesting and look at how does procedural reuse work. Okay, so some of you may already be familiar with the concept of a Siamese twin or a Siamese neural network. Its typical application is like in a product category. Okay, so let's say let's say I'm a company and I have 100 products, and let's say they're clothing, 100 different types of clothing. Okay, and I got I got a handful of images for each one, and I train a model. Let's call it this model here, how to predict given a picture, which one they are. Okay, now here's the problem I want to solve. An end user, a customer that has their own picture or something, and it's not one of your products, but you want to know what's the closest product you have that looks like their picture. Okay, and that's what we use a Siamese twin for. Okay, so the basic idea is you have conceptually 2 copies of the model. You really only have one. They're shared layers, but pictorially we show it as 2. And you take the first input, which is this user picture, okay? That isn't part of the training data and is probably not one of those 100 categories. But it's going to go through an already trained model, okay, that was trained for those 100 categories. And before you get to the task, that is, you get to that very last stage of those final feature maps, you then do that global average pooling, so you go from the encoding to what's called the embedding. If you recall what I showed you way back with those 4 outputs, so you get that low dimensionality latent space for that image. Then you take a reference image from the other categories. Let's say if you have 100 categories, you're going to take 100 reference images, pass them through here, and get their latent coding in space. And then you're just going to do a simple L1 distance test between the vectors to see which of these 100 vectors is the closest to that vector. And the one that's the closest is blah, tag, you're it. Okay? And that's how it does its comparison. Of course, you can do this much more efficiently. There's no point if you have 100 of these images each time somebody loads a picture rerunning 100 reference pictures. Okay, it's kind of ridiculous. Okay, instead we have a database. So ahead of time, I've taken my model here, and for all 100 categories, I've ran through a handful of reference pictures to get their latent space for that category. I call the average latent space for that category, and just saved it in a database. Okay, so now when I do in real world the equivalent of a Siamese twin, I only have the one model. I run my new picture through it. I get that, low dimensionality embedding of the latent space. And then I just call the database, could be an SQL database, give me those 100 vectors, and then do a quick, matrix L1 distance comparison. So yeah, so let's get past that. Okay, hierarchical nets. Okay, so let me see if I can get a good picture here. Okay, hierarchical nets is a special case of multi-labeled data. output. So you remember before I talked about what about you're having a model that predicts more than one type of class. So it might say it's an apple, and then it says it's red, and then says how ripe it is. And so you had 3 separate tasks in there. But what if they were hierarchical, the labels? One says it's the type of fruit. It's an apple, and the next one is like the variety. It's a red apple or a granny apple, etc. And you have this hierarchical relationship. Okay, so the way we do that is we actually attach the output, okay, from like usually the dense layer that's going to make the prediction on the type, and make that an input to yet another set of tasks. But each one of them will have, for every category, will have its own task. So let's say I had 32 different types of fruits. I would have 32 separate task components for the variety. And I'd have a switch here in the model that if it predicted an apple, then that result would get set here to try to predict the variety, etc., etc., etc. And of course, it's not really the probabilities I'm sending here because I need more information. I'm going a little bit earlier in this task here where there's multi-outputs, and I'm probably going to end up sending the embedding over to it. Let's see. Yeah. Effectively, it's just another way of showing it. Okay. Alright, this is kind of just showing you conceptually how the idiomatic procedure reuse can be fitted to object detection models. So this is one of the early granddaddies of them, called Fast RCNN. And now there's a whole bunch of variants. Okay. I think this one is about 2016, but it was used for a very long time. Okay. And it just shows you how the concept works in object detection. So you have your images. You push them through here to do that first preparation. I get asked this quite commonly. I'm not sure somebody asked already this one. So images and object detection are generally, we have to use larger size images so that we can find small objects in them. So typically the input size is more like 600 by 800. Okay. And then we're going to have our convolutions here where we're going to get those feature maps, right? So we get down to some, you could say, latent space. Okay. And then we're going to do, we need some method of proposing bounding boxes, candidate bounding boxes. Okay, RCNN used a very early technique called selective search. There's a lot more other ones today you can use, but the principle here is it's proposing regions within that image that could be an object, and of course with that region it's proposing it as a bounding box. Okay, then it went through another stage called region of interest pooling, where it's kind of coalescing them together. You know, if you have a whole bunch of proposals that almost entirely overlap with each other, you might as well just reduce them into a single proposal. And that's what region of interest pooling did. Now I got all these proposed regions. There's also another step that happened here in selective search, where it tried to predict the likelihood of a candidate being a foreground object, okay, meaning it has a being a foreground or a background. Foreground, it means it has an object in there that could be classified. A background, meaning it doesn't have an object in there, could be classified. Obviously, all the background candidates get filtered out. So you only have foregrounds coming here. You're going to then pool them into a subset. And then finally, you're going to learn 2 tasks in parallel. Classify what was in that candidate foreground bounding box. And then a bounding box regressor, this is a regressor, that's now going to fine-tune the bounding box around that object. Okay. Yeah, that's just going more into it. Okay, maybe I can show you UNet. Okay, this is one of the first early successful image segmentation models. Okay, again, you can totally put it together using the procedural reuse design pattern. Okay, in this case, it has two different types of groups in it. One called contracting groups and one called expansive groups. Contracting just means that feature maps got smaller, smaller, smaller. And expansive groups means they just got bigger, 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 bigger. If you're familiar with autoencoders, it's kind of like an autoencoder on steroids. Okay, so let's kind of just look at the contracting groups. Okay, so there's each group is going to progressively double the number of filters. Well, that's the output feature map, so that does that consistently. But as it's doing it, it's also progressively reducing the size of them. So while the number of feature maps is going out, their size is progressively getting smaller. And that's the contracting. But we also remember the output from every one of these instead of a single output. So up to now in a regular CNN, this was your only output coming out of the learner. Now, in UNet, every group has its own output. So if I have 3 groups here, I got 3 outputs plus the final output from the group. Okay, so the expansive one, okay, basically does the opposite. Everyone doubles the size of the feature maps, but reduces their number by 1/2. Exact mirror opposite. Now the interest is, where is the input coming from? Okay, so this arrow means that yes, the output from the contrasting one becomes the input here, and it is driven through. All these other groups take a second input, not just this primary input, but an input that's specific to the mirror on the contracting side. Okay. So probably won't go too much longer. I don't think I'm going to use up the whole 2 hours. Okay, I'm just going to cover one more thing. How to do this as an autoencoder. Okay, so in an autoencoder, you have 2 components. You have the encoder and the decoder. Okay, and generally what we have here in the middle is what we call the latent space. You've been hearing me say that a lot. And the job of the encoder is to learn the best way to progressively pool your input into the latent space such that the decoder can learn how to progressively unpool it and reconstruct it to something. Okay, so this also introduces new terms of transformational learning, and that's your reconstruction. So instead of the label, the output being some predefined label like apple or elephant, it's some reconstruction of the input. Now, the simplest reconstruction is the identity function. The output is the same as the input. This is how people first learn autoencoders. They think of it like learning a compression algorithm for a specific data set. You know, what is the best way to compress that data set? Okay, this latent space is the, compressed data. So the encoder is the compressor, the decoder is the uncompressor. But this reconstruction can be other things. Okay, super resolution, for example. What if I want to train my neural network to take low resolutions and output a high resolution equivalent of it? So what I'm going to train is I'm going to start with high resolution images, okay, and I'm going to intentionally make a copy of them that's low resolution. And I'm going to take that low resolution copies as my input, And my labels are the original high resolution ones. And the task I'm learning here, the reconstruction task I'm learning here, is that transformation from the low resolution to the high resolution. Yeah. Okay, so let's just kind of take, this is just a more detailed look at that, but that was a generic version. Okay, so one of really the very early successful ones was the deep convolutional autoencoder. Early ones used dense nets. Dense layers. They were very minimal in what they could do. But once we went to convolutional layers, it made a big difference. Autoencoders are using all kinds of things now. Okay, but you're still doing your learned pooling and your learned unpooling. Here you're doing them with convolutions. Here you're doing with the inverse of convolutions. That's a transpose convolution, or sometimes called a deconvolution. We now refer to the encoder as doing representational learning. You're learning the best way to represent this input in the latent space of substantially reduced dimensionality, so that you can then do transformation learning to accurately do your reconstruction task. Let's see if there's anything more, because I think I'm going to go up and wrap up a little early. Yeah. Okay. Yeah, if I went any further, I'm going to start getting into other parts of the book, and the title in this section was just to give you an introduction to the design pattern, the first design pattern I show in the book. I show many more after this. Okay, I'll give people a chance to ask any last final questions, and after that, I'll just give people back their what looks like would be a remaining half hour. Or if somebody wants to just post what they thought of the presentation. As you know, this is my first time doing Twitch. Okay. Well, I want to thank everybody for attending and for the questions you asked. And I'm going to go ahead and let everybody go now.